my tribe is anthropology. I'm really interested in how people work. And when I discovered chatbots initially, quite a few years ago, through Facebook Messenger and stuff like that, it got me into natural language processing because you can extract meaning from text and start to look at how people work and join all together. And that led me on a path that's taken me here. So not. There we go. Oh, this is my profound piece from
Into a number. 3. You graph the numbers of any system, patterns emerge. Therefore, there are patterns everywhere in nature. This is insanity, Max. Or maybe it's genius.
So hopefully some of you will recognize that as Pi, Faith and Chaos, which is a superb, absolutely superb movie. But it's all about patterns and patterns in numbers. And one of the things that I often think about when people are talking about AI and machine learning is that Arthur C. Clarke quote, the one about technology and magic. The other thing that I often think about is the pre-Reformation church, when only priests could speak to God. People like to make artificial intelligence and machine learning more complicated than it needs to be. At its heart, it is very, very simple. It's pattern recognition at scale, at a scale that we are incapable of doing. And the algorithms that are used to recognize these patterns then allow us to make predictions, classify things, make decisions, and in the case of generative AI, make plausible fakes, which is what generative AI is all about. So what makes all this possible is data. There's this idea that if you throw a load of data into an AI system, you're going to get meaningful results. Politely, garbage in, garbage out, or shit AI. So if an AI system is only as good as the data it's trained on, that means that the foundations for any successful AI project are based in data, and not just any old data, good data, where quality matters more than quantity. Now, if we're looking at generative AI, where did all this information come from? Well, it started back in the good old days of 2007 with a project called Common Crawl. And what Common Crawl did was it was a bit like a digital explorer. It scoured the internet, downloading text from every web page it went to. And initially, this was just a nice, sleepy little research project. It was used by academics primarily. Saying that they downloaded the internet, that's not quite right, but it isn't far off the truth. Then, about a decade later, the generative AI companies came along and went, what's this we have here? A massive data set of text. So, huge amount of data there. Oh, huge amount of data there. Quite a lot of it garbage, though. The So I'm going to just run you through the process that Hugging Face went through to build their fine web data set. And OpenAI, Google, etc., will have some variant of this. They will go through a very similar process. And if you want to read more about it, Hugging Face have a superb blog that's really extensive and really detailed. But for the 10,000-foot view, what they did was they dropped out all the garbage. They dropped out the Jane Austen erotic porn. They dropped out malware sites. They dropped out spam, extreme sites as well. You don't want your language model spewing this out to the general public. That would be disastrous from a PR point of view. Then they started going through a process of text cleaning. So from the common crawl sites, dropping out HTML tags and that sort of stuff. Some basic text cleaning, and you've got a cleanish data set by this point. Then, because FineWeb is focused on English language, they did an English language filter. So they said if the web page wasn't more than 65% English, then they were dropping it. There's another series of more fine-grained filters that are doing things like deduplication of the data set, removing personally identifiable information, etc. And what they ended up with was a data set with about 15 trillion words and 44 terabytes of data, which actually isn't that much when you think about it. You could probably fit that on a few hard drives if you really wanted to and carry it around with you. So the next step, so this is a quote from V, and I will just walk you through the process of how we go from messy human language to something that machines can understand. Text from the internet isn't AI ready. Computers don't read the way that we do. They like nice symbols, and they like them to be nicely structured and formatted. So before we go and train our neural network, we need to do something about that. And I'm sure most of you in the room are thinking, binary underpins everything, right? So every letter, punctuation mark, white space is represented on the screen here in those nice little blocks of 8. But there's only 2 symbols. You've got a vocabulary of 2. And passing all of this into a neural network is computationally expensive. So we need to make a bit of a trade-off. And the first sensible step is to go from bits to bytes, right? Makes sense? And that means we have an ID for each white space punctuation letter. And I encourage you to think of it that way. These are IDs, not numbers. But think back to the FineWeb dataset. That's 15 trillion words. So 15 trillion times the average length of a word. That's a hell of a lot of IDs. So we still need to reduce that further. And if you look, you get bytes that appear very commonly together. And we use what's called a byte pair algorithm to identify it. We start to expand our vocabulary. So at the moment, we've got 0 to 255. But let's start to trade off. Instead of saying 101 and 32, you can say 256. Instead of saying 32 and 116, you can say 257, and so on. And researchers demonstrated that actually what we're looking for is probably about 100,000 symbols or IDs. And that's the optimum point of length versus vocabulary size. And those of you who are familiar with LLMs will know what I'm talking about here is tokens. So words are represented to the language model as tokens, not as words. And if that speech from V is converted into tokens, that's what it'll look like. I should say as well, these tokens capture everything. So if you change things from uppercase to lowercase, fiddle around with the punctuation, white space, you will end up with a different token representation. Now it comes time to train the model. And what we do is we take random lengths and sequences, tokens, and pass it into our model to train it. And what the model is doing is then telling us the probability of each of those 100,000 symbols, those 100,000 IDs coming up next in the sequence. Theoretically, we could take unlimited lengths of sequences, but this is where we start to hit up against the context window. So it becomes computationally expensive, which is why, like GTP4 says you've got a context window of 8,000 tokens, because that was the context window they decided on when they were training this. So they took up to 8,000 tokens to train in the pattern. So we've got our pattern now, and it's generating or telling us the probability that any token is going to come next in sequence. But so in this case, these three tokens here, and the neural network is telling us that probability of the next tokens coming up is 4, 3, and 2. Just as an example, this is not accurate at all. But we know from looking at the data that actually the next word is as. So we're going to go and fine tune it. We're going to tell the model that actually we know from the training data that the next word or the next token is not 22, 25, both. We know that it's 439 as. And that's us doing what's called fine tuning. We're adjusting the weights, or I like to think of them as parameters that we're passing into our model. It's helping the network, the neural network, reflect what we want to do better based on the data that we're providing it. Something that I've skipped over, and actually a lot of people skip over, and this is kind of fundamental, is that a neural network is just a mathematical expression. It's very long and integrated, but it's not complicated. It's not massively complicated maths, really. It's just the way it's put together. And into that mathematical expression, we're passing our tokens, and our parameters or weights that will affect the probability. And again, what comes out is just a list saying this is the probability that this is the next token. I hope some of you know what I'm about to talk about now. What we know as large language models are based on an architecture called transformers. And if any of you have read the paper, Attention is All You Need, from back in 2017, this is what one looks like at a very basic level, and they're made up of two parts, an encoder and a decoder. And what the encoder does is it converts those tokens along with positional information, I will go into this a little bit later on, into a vector, which is just a list of numbers. And it's a predefined set list of numbers, so it will always output vectors of the same length. And that's what we use for like classification tasks and so on. The decoder bit is the bit most people are probably more familiar with. It's the bit that creates or generates new text. And both of them together is how Google did Google Translate. So, actually, I should have said as well, the vector captures not just, like I say, not just what's in the word, it captures the meaning as well through this sort of positional reference. So it relates how how the tokens relate to one another. Um, anybody else feeling a bit like this? That was a lot of information condensed quite. I'm just making the point that I made on slide 1. Pattern recognition at scale and generative plausible fakes. It's not the right answer. And it feels really detailed, but actually understanding that will give you a better idea of why LLMs hallucinate, which, while we're on the topic, so firstly, no, LLMs can't lie to you. I'll tell you why in a moment. But I really dislike the term hallucinate, and the more I think about it, the more I dislike it. That's for 2 reasons. And the alternative words, I mean, I've heard people talk about delusions or bullshitting or making stuff up. Language models don't do this, right? The first reason I dislike it is that it's to do with my background in anthropology. You're conveying something on a mathematical model that shouldn't be there. You're giving it intent and beliefs. Mathematical models don't have intent and beliefs. You're straying into what I think of as dangerous territory. You're starting to anthropomorphize this mathematical model. We can dig into that later on because I think that raises some interesting questions. But more importantly, I think the term hallucinate implies something about the model not working, that there's some sort of flaw in the system. I strongly disagree with that. I think hallucinations are representative of exactly how the system is working. The fact that it's doing that means it is working, even when it gets things wrong. So is everybody in the room familiar with family fortunes? Yeah. So what happens is it's a game show. There's a question up on the screen that has multiple possible answers, and then the family members have to say, I think it's this, and you get points based on members of the public agreeing with what you said. And for me, that gets to the crux of the matter. It's really, really critical. So LLMs are using that pattern they established to create, to suggest the next probable token. And that's what most people get wrong. There's significant effort gone into training these models to predict the next word. They're not trained to ensure factual accuracy. And that's a crucial distinction. We need to think about the training data. I mean, there's 44 terabytes. That's a lot of information. And I don't know about you, but I'm not going to sit and dig through 44 terabytes of web pages and check that it's all factually correct. I can tell you that a significant amount of it's going to be bollocks. And so through that training process, it's inevitable that the model is going to be exposed to information that just isn't correct. Also, we're talking about truth here. Mathematical models aren't, or mathematical expressions they can't tell you what's true and false, and certainly they can't deal with any of the shades of gray in the middle. It's a very complex thing. So language models, they're not search engines. They're not databases. What they are is sophisticated language calculators. And just predicting the next word in the sequence. They're not reliable information repositories, and we, as a society, we need to stop thinking of them that way. And I'm firmly of the belief that actually, if we start looking at them as an interface, that changes the dynamic massively. So when you're designing a system based on language models, I would strongly suggest that you take advantage of what makes them so powerful, that predictive element, but you need to control the hallucinations, the bit that makes them wonky. So how do we do that? Now, people get caught up in this bit. This is the bit that makes people excited. This is the bit that everyone speaks about. And I really love this technology. I think there's some really exciting engineering. There's some really brilliant innovation going around. But for me, magic sits here. And I think some of you might be a little bit confused, but I'll elaborate in a moment. But to make sure that you can trust what an LLM or a language model is telling you, you need to make sure that it's getting its information from a grounded truth, that you can rely on the information it's feeding you. And that's the dirty little secret of language models, is to get them to work effectively. You tell them what you want to hear from them. I like to think of them as an articulate buffoon. So how do we go about serving up information to the language model? There are a few methods out there. You could get the language model to compose the database query for, sorry, you get your information from a database, right? I mean, that is, you know that what you're putting in there at least has some basis in fact for you or your company. And you could get your language model to construct a database query for you. There are plenty of data sets out there that will allow you to fine-tune your models to do this. I don't think it's worth a return on effort at the moment. My preferred method is retrieval augmented generation, or RAG, and it's a term that I think you probably will have heard of. And RAG needs to be backed up by vector databases. So that comes back to what I was talking about earlier about vectors capturing the meaning and the semantic information on the text. So if we go back to our transformer model, we're only interested in this bit. This is the bit that generates the vectors, the bit that converts the text into something that we can search and that we can use. And it works a bit like this. So you get your tokens, your positional information, and then the neural network will convert that into the standard vectors of fixed lengths. And it captures much more semantic information, captures the meaning and context of the language, which is so critical to understanding it, which earlier techniques like TF-IDF and bag of words really didn't. And once we have vectors, we can store them in a vector database, which sits at the heart of any AI system. So when we're dealing with any RAG system, we've sort of got, or retrieval augmented system, we've got the starting point, which is the vector database, and we need to go through an ingestion and retrieval process. The ingestion process, we are looking at probably populating it with documents, and there's a couple of strategies that we can look at here. How do we break up the documents so that we capture the maximum meaning and the maximum, and not lose anything to the noise? We need it to be contextually there, but also specific. So we could break it down to sentence level, paragraph level, whole page level, but we're making compromises there. I like a technique called context-aware or semantic chunking, where you use the semantic structure of the text to group it together. So you're not going, right, after 300 words, I'm cutting it off. I'll maybe include a bit of overlap there, but 300 words, no. It ensures you've got the context, you've got the ability to search more accurately, you're providing more specific information. So after we've broken it down, we've got those contextually aware chunks of the document. We can then convert them into vectors and store them in the vector database. The next bit is retrieval. So when we're talking about retrieval, It's not SQL where lookup. It's not more complicated. Actually, I think it's probably simpler than an SQL database. What you're doing is you're taking the input vector, which is coming from the user. You're converting that through the same model, and this is critical, that you use to populate your database with. And then you compare the two vectors, and handily, this is largely done for you by the vector database. They use something called approximate nearest neighbor and cosine similarity to retrieve that information. And to make it easier to understand, I personally like to think of it like a map. We know that Aberdeen and Dundee are more similar to one another than they are to Riyadh or Kuala Lumpur, purely by dint of geographic proximity. They're near one another, so they're going to be similar. And that's the way that retrieval works in a vector database as well. Except it's just, instead of a 2D map, it is like hundreds or thousands of dimensions are being compared here. Impossible to visualize. So that makes it a bit easier for me. Back to the RAG architecture. So user query goes in, gets converted to a vector, compared to the vector database. The information then gets, the most relevant information gets passed from the vector database and added onto the query using something like, use this information as context when answering my question. And then it then goes from there to the language model, which now knows its answer is grounded in fact. Well, it doesn't know. You know that it can answer because its answer is grounded in fact, and that you're going to benefit from that articulation exercise. Before we move on, there's a critical element that hopefully eagle-eyed people in the audience you'll have spotted. I haven't mentioned guardrails, and I think they are fundamental to any language model-based system. They're what keeps your system reliable and on point, from both the queries being asked by the user to the responses being given by the system. If you cannot, I mean, I don't know about you, but I probably wouldn't want users having a conversation with my language system and discussing extreme politics of any origin. I want it to be talking about the purpose it's there to serve up. There are quite a few options. So off the shelf, Nemo, guardrails.ai, you can build your own if you want. It's not particularly complicated, but it does ensure that your system is behaving reliably and predictably, or it helps. Right, so if you get all of this implemented, what do you have? You've actually got something quite powerful. You've got a retrieval and summarization system that can be built to be topic specific. So imagine implementing this in your company where you processes, procedures, all that sort of stuff, being able to interact with it through a Teams bot and say, I need this, I can't remember what the procedure is called because it's some stupid number, right? You can say, this is describe, retrieve, bring back, and summarize it for you. I would also advocate putting a link into the source data in most circumstances, so that the user can verify the information. Now, what we've got is quite powerful, but we can do better. Is anybody in here familiar with natural language processing at all? Okay, so perfect. So I'm a really big fan of what's called named entity recognition. I think it's incredibly useful. And if you pair it with a large language model and a vector database, it makes everything just that more powerful. So what named entity recognition does is it extracts key entities from text. So in this case, person, location, organizations, and it gives you additional context with which to search your database, essentially. And if we pass, prior to vectorization, if we pass it through an NER model, we can extract relevant entities. So I'm working on a project for mountain rescue at the moment, and what they're interested in is equipment, weather conditions, party size, environmental conditions, stuff like that. So pulling that out using NER gives us a much more searchable system because we tag it onto the metadata for the vector database. Okay, and then it's the same when at the retrieval stage. The user query then goes through the named entity recognition system, pulls out the named entity, and we use it much like a where clause in an SQL database to allow us with a much more powerful filtering mechanism rather than just relying on the semantic structure of the vector. Right. If you're designing this sort of system, you need to think about short-term memory as well. Language models are inherently stateless, which means they treat each query independently. They don't remember the last thing you asked them, and you have to design that into the system. There's debate about this. I definitely fall down on the short-term memory side. I think that context is intrinsic to an effective system, at least 15, 20 minutes. You've got a few strategies here. You can pass that whole conversation in, but you will hit up against that context limit fairly quickly. You could summarize the conversation and pass that as context, but then it's going to cost you more. You're more reliant on the language model systems, and there's trade-offs to be made. And for me, the most effective strategy is what's called the buffer window method, where you only retain the most recent interactions. So that should hopefully provide you enough context for what the user needs next, but it will forget the first part of the conversation. Slightly, not always. Last presentation I was at, I said, fuck no. And this is something that search engines have known for as long as they've been about. So they've got techniques that they apply to augment your query to return more useful results. So they'll do things like synonym expansion. So if you're searching for car, you'll also add automobile into your search term. If your search, they'll do things like stemming and lemmatization, which means looking at the root of the word. So if you are looking for running equipment, they'll strip it down to run and add that onto your search term as well. There's a few nifty little things and that you can borrow, and actually it's a really quite a good idea because, yeah, users don't always know what they want and they don't know how to articulate it. No, I'll skip that. So we've expanded our query. We've added dynamically. We could even use the LLM actually to say, can you suggest alternatives, and send multiple queries to our database. So now that we've done that, we've got to process and find results that are on target. So we need to rank results somehow. And again, quite a few strategies to do that. The one that I personally like is called cross-encoder re-ranking, where you use a model to combine the query and the result into one embedding, essentially, and it captures sort of the relevance in there, and you can then use that to re-rank your queries and just, extract the most relevant ones and ones that come top of that priority list. It means you're serving up the best possible information. There's always a trade-off, right? So cross-encoders are slow, and it depends on what you're looking for. In most circumstances where you're looking at this sort of system, I would suggest you're looking at maybe technical documents or documents that small changes can significantly impact the meaning. Right. Fine-tuning. It's funny, I see everywhere articles, RAG versus fine-tuning, which to me seems like these techniques are being presented in opposition to one another. And yeah, they are. They're in opposition to one another, and they're opposition to one another in the same way that the fingers and thumb of my hand are. They are an opposition by which I can grasp anything, by which I can tackle the most complex challenges, working together. So these techniques aren't alternatives, they're complementary. Though I would say that if you are looking at fine-tuning, consider RAG first. It's easier and cheaper to implement. And also, if you're looking at fine-tuning, seriously look at small language models so that you can train them to be task specific. There's another bunch of good reasons for looking at small language models, but I will let you put that on your own. And finally, this is my own little bias, actually. And it's sort of linked to my anthropological background as well. I believe that the whole world's interconnected, the 6 degrees of Kevin Bacon. And one of the areas that RAG really struggles with is where documents are quite similar. We are mitigating that with the named entity recognition, but I would suggest if we're going to that level, it's worth looking at a graph database. And all the graph databases they're just a data model where everything's connected through nodes or entities, edges or relationships, and attributes on them all. And it allows the system to access information that is connected, spread over multiple documents, or where documents are very similar, but there's fine differences. It is worth having a look at, and I'll let you Google it. So I firmly believe that what I've talked about tonight isn't just a domain of tech companies. I think that any company, irregardless of size, can do this. There's plenty of tools out there. There's ChromaDB, Hugging Face, for graph databases, Neo4j, Tigrograph. The only real limit, once you start exploring this, is your imagination. And I would like to see people in this room really pushing this frontier because it's hugely exciting. Now, remember, generative AI at its core is about pattern recognition to produce plausible fakes. I hope I've made that clear this evening. You can use fine-tuning to make it more domain-specific and better, but the real magic for me, like I said, is at that retrieval stage where you tell the model what you want it to tell you. Articulate idiot. But reliable AI isn't just about generation. It's 90% orchestration, if not more. And it's true that generative AI is only going to get better. It's going to get better, it's going to get cheaper, and it's going to become more effective. I have no doubt about that. But the mindset that we need to have is round about that orchestration piece, because as the generative AI gets better, as long as we have good orchestration, the generative AI is only going to add to that. And the thought that I end all these things on is that it's only a tool. Everybody in this room and beyond has responsibility for that tool, how it's used, and what is done with it. So QR code to the Fine Web blog, transformer architecture, and then that big one in the middle is to a repository I set up, which will allow you to experiment with vector databases. There's documentation there for Hugging Face, for Streamlit, ChromaDB, and it'll allow you to do that document retrieval bit. I've got a sample data set of news article headlines that you can experiment with as well. I would strongly advise that you have a go, because it's actually fairly easy, and it's not as complicated as the priests make it seem. Thank you very much.
Before we move on to the kind of practical aspect of tonight, are any questions in the audience? I'm going to use this microphone so the folks at home can hear what we're saying.
Great talk. I want to learn more about the named entity recognition.
Okay.
I'm struggling to see exactly the benefit of that. Maybe I've not quite understood properly, but from my understanding is that it extracts the nouns from a prompt and then it passes it as context again to the.
Essentially, yeah. So it just allows, so for me, it's about that filtering down of the information that you're being passed to make it more specific. So in the case of a system like this I did for the oil industry, it was extracting information like drill bit names and well names, etc., stuff like that, and it allowed me to then say, if the vector database has these in the metadata, pull those back only, because without it, it was saying this sentence is very similar, or this bit is very similar to this one, which is actually for a different well, or it's about a different drill bit. So just about that fine tuning, the information returned.
So I guess it removes the nuance.
Yeah.
Cool. Thank you.
Thank you. Yeah.
Language is beautiful. It's colorful. It's
Yeah.
nuanced.
Yes.
Are LLMs going to drive us to standardize BBC English? And we're going to lose out as a culture and a society as a result of this technology?
I think that's a really good question. I'd be lying if I didn't say that was something that niggles at me. I think culture generally is beautiful, and language is a critical part of it. So that move, and it won't be BBC English, by the way, it'll be American English, because that's what dominates the internet. There's a big drive to make language models more language specific, but because, and hopefully this is something that sort of gets resolved, because because the language of the internet, the lingua franca is American English, I think there's going to be a move that way. What's quite interesting as well was I had a conversation with somebody at RG Youth Hackathon, where she was talking about what would be interesting is to research how interacting with models changes the way that you're talking in everyday language, and actually, especially for the generation coming through. And off the back of that, I actually went and did a bit of research, and there are plenty of papers out there about how people are starting to be more direct. Their sentences structures shortening. There is a change that's come, and 2021, 22 for ChatGPT. That's a very short space of time, and I don't know if that answers your question, but I think there's an awareness actually generally, I think, around this technology. I think there's a massive lack of literacy in this area, and I think that is one of the topics that should be part of that, is retaining your own cultural identity, which could be quite difficult.
Any other questions in the room?
Yeah, I think the point you made about orchestration is an important one, because for technology providers in the room, and those that want to work with these things to build solutions, that's where you can add your unique aspect of your solution building in the orchestration part. I think to help that, what we should hopefully be seeing as this technology evolves is some sort of disclaimer or certification, if I call it that, or maybe audit or whatever it is, to reveal behind the scenes what this black box is actually doing in any given context. So for example, it can say, well, actually, this black box here is constructed of this LLM plus this, there's a whole chain of things that happens to your data as it flows through. to reveal exactly what's going on. I think, to be fair to end users, we should start seeing that happening, because the end user just doesn't have a clue what they're
No.
getting data into. And actually, the problem is at the moment, from the enterprise that I speak to, they're just putting the shutters up completely. So actually, the only thing that large-scale enterprise is willing to even entertain at the moment is Microsoft Copilot, because it's built into the Office suite.
Yeah.
But it's not necessarily the best solution. It's actually quite filtered down to the point that it's very limited. But I think your point was well made, in the sense that if your competitive advantage is your authenticity. That's what we're saying here, is the authenticity is the competitive advantage. And if you can get the good quality data, so you have to start at the very beginning. How can you get good quality data captured, stored in a very good structure, in the best schematic structure that you can, to be indexable, vectorized, and then used in the ultimate solution. I think that's the key message, I think, to drive home today.
I'm not going to disagree with any of that. I think you're spot on. Yeah.
Sorry, it wasn't a question. I'm just summarizing what you were saying.
Very much. So I'll just speak to the area Arash just mentioned. So currently there are research being done correctly on what is called explainable AI. Okay, so you want to know what goes on behind the scenes. So you just don't rely on what the model is saying. Okay, so that's for the future, and it's part of what researchers are looking at. Okay, that's to address this question. So I've got another question. So the question is there, in your own thought, okay, so which would you recommend for a company that's interested in building a language model? Should they do it based on their own data, or throw the data open to publicly available data sets?
So that's a really good question, and I think it comes down to the use case. If you're wanting something sort of just generally generic, publicly available data sets, fine, whatever. If you want something task specific, and this is again, like I said, where I'd be looking at small language models, I would definitely be looking at fine tuning. It depends on the size of the company as well. I mean, there's a whole load of factors come in here. But I would definitely be looking at doing at least a degree of fine tuning for whichever model I selected. I wouldn't just be relying on publicly available information. And I think it comes back to what Arash was saying there as well, about that initial data acquisition phase is so critical and is often ignored. It is that, well, here, have it. The world's been very guilty of just saying, I'll fix it with AI, I'll fix it with machine learning, I'll fix it with computers, but there's a structure there. So that first stage is making sure you have data that isn't accessible and makes sense. And then the next stage is that, what's your purpose for? Is it fine tuning? Or is it just generic question and answer for procedures? If it's question and answer for procedures, like HR procedures or whatever, then I probably wouldn't even do any fine tuning. I'd just use something off the shelf. If I want it to be looking at going back to what I was talking about, well information, so I can use that for forward planning in executing drilling operations. I'd be looking at fine tuning a small language model that I was storing securely on my own data for sure. But actually, the point I would like to come back to the earlier point as well. This is going to make me sound like a bit of an arse, but if you're not in a position, so you're about the explainable AI, how it gets the answer, yes. But actually, if you're not in a position to assess whether the information coming out the other end is credible, should you be using it? I don't think so. I think if you're relying on the information coming out to make judgments on an area that you don't have enough knowledge in, you're up a creek without a paddle. And it is one of these things, and I sort of I'm doing a mentoring program with some kids from of high school age, and it's actually a bit worrying how many of them are not critically thinking about the answers they're getting back. They're just going, oh well, it's got to be fine, right? So there's a whole raft of issues here. Critical thinking, I think, being at the heart of all of it.
I'm just going to have one final question before we move on to the practical session. So from the people at home, I've got, which do you think is better suited for compliance, fine-tuning, RAG, or both?
I would start with RAG. Mostly because it's the most straightforward to implement. You don't need the same amount of compute resources. You don't need the same amount of technical expertise. You don't need the same amount of time. And it's going to be about experimentation ultimately. I think in terms of compliance, you probably will end up with a mixture of both. But again, it depends on your use case. It depends on a whole bunch of factors. And the only way you're going to find out for sure is experimentation. Which I think leads us nicely into this, the practical session. I'm going to put a disclaimer in here, by the way. I did not test any of the code that I put in there. So I did it in a bit of a rush. So you may find bugs and uncommented code, I can't remember, in the examples. But thank you very much for having me, everyone. I really enjoyed myself this evening.
Okay, so as you can see on the screen, there are some, oh God, I'm on the camera now. The big QR code. So those of you who've brought a laptop, have a go at the practical. I think I've got a short URL to this on my slides. I'm going to jump out of this one.
No worries. Hang on, I'll stop sharing.
Yeah. I'm going to stop recording.